Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to continue learning about operating systems, the topic that we call process management. This is part 2 of the series in these presentations, which are running from part 1 to part 4. And therefore, it is my expectation, my dear learners, that you have been able to go through the operating systems process management part 1 series or part 1 video in which we discussed about the meaning of a process, the importance of process management, and we also looked at the various concepts that are related with the process management. And therefore, in this presentation, which is part 2 of the series, we are going to look at the process states, the process models, and process scheduling. My name is Meme JM, or you can call me Emily Swap. So in this presentation, we are going to look at the process states, which we are going to look at the new state, the ready state, the running state, the blocked state, suspended versus waiting state, suspended versus blocked state, and terminated or exit state. Number 2, we are going to look at the process models, and our attention will be focused on the 2 states, 3 states, 5 states, 6 states, and 7 state managed process models. Lastly, we are going to look at the process scheduling, where then we are going to look at the various types of scheduling algorithms, which include the non-preemptive and preemptive scheduling algorithms. So what are process states? Each process moves through a number of phases from entry into the system until it completes or exits. The process states are therefore the phases through which a process passes from the time of entry into the system until it completes or exits, while a process state is the current activity of the process. The state of the process is also known as the status of the process, and each process passes through various states. The status includes whether the process has executed or whether the process is waiting for some input and output from the user to run the program after the completion of the process. The process state consists of everything necessary to resume the process execution if it is somehow put aside temporarily. And therefore, the process states consist of at least the following. Number 1 is the code for the program. Number 2 is program's static data. Number 3, the program's dynamic data. Number 4, the program's procedure call stack. Number 5, the contents of general purpose registers. Number 6 are the contents of program counter. Number 7 is the contents of program status 1. And number 8 is the operating system's resource that is in use. This complete information about a process is stored in a section of the memory forming the process control block, PCB, that we looked at in topic 1, part 1 in this series. So whenever a process executes, it changes its state. Whenever a process changes its state, the operating system reacts by placing the process control block in the list that corresponds to its new state. Only one process can be running on any processor at any instant, and many processes may be ready and in waiting state. My dear students and the rest of the learners, in process management part 1 of the video that is already posted in Emily Swap ICT YouTube channel, I said that a program is the set of instructions that have been written by a programmer using a certain programming language in order to tell the computer what to do and how to do it. And this set of instructions are stored in a secondary storage medium, such as hard disk. But when the user wants the computer to perform what has been written or coded in form of a program, a copy of that program or a copy of those set of instructions have to be loaded into RAM, from where the central processing unit can be able to process them. And therefore, we said that a process is a copy of the running set of instructions. And therefore, we said that for the processor to be able to keep track of a process from the time it is created to the time when it completes execution, the process manager develops a process control block that contains all the information concerning or about a process. And therefore, when a process changes its state, the current state for that process is indicated in the process control block under the element that we called state. When you go through the part 1 video in this series, there is a diagram on process control block and the various information that is found in it. And one of that information is the state of the process. The following are therefore the main states through which a process can pass. The very first state for every process is called the new state. This is the initial state of a process once it's first created or started, and it awaits admission to the ready state. When an operating system is booted, typically several processes are created. Some of these are foreground processes, that is, processes that interact with the users and perform work for them. What this simply means, my dear students, is that you should always note that any activity that takes place within a computer is as a result of a circuit in your computer. There is the very first process that has to be loaded in memory, and that process is the process that concerns or relates to operating system. This process has to be loaded, and then it is executed so that the processor can be able to know whether the computer and the basic requirements are available and functioning well. And therefore, that is a simple indication to inform you that even before you start your own user process, like loading an application, there are already other processes that play certain roles from the background, and some of them are created or initialized once the booting process has taken place, so that they are able to perform certain functions. Others are background processes which are not associated with particular users, but instead they have some specific function. An example of such a process is the antivirus process, which runs once a computer is booted, so that the system can continuously check or can continuously ensure that there is no threat to the processes that have been loaded, that the system is safe and secure. And therefore, an antivirus process is a very good example of a background process, plus other processes, such as those processes that concerns various functions of the operating system. The background processes stay in background sleeping, but suddenly spring to life to handle activities such as email, web page, printing, and so on. Background processes are called daemons of the calling process. A process may create a new process. A process that creates a new process is called the parent process, and the created one is called the child process. Just as we said in part 1 of this series, we said that once a process has been loaded, an example which I gave was Microsoft Word process. We said that the purpose of this process is to create files or documents. And we said that when Microsoft Word process is loaded and the user creates a file, in this case, the file that has been created using the Word processor process is a child process. And therefore, we said that Microsoft Word in this context is the parent process. Another example of a parent example, you have loaded a Pascal process. Using the Pascal process, you can be able to code or create a program that can be used to execute a certain task. For example, you can create a program that means you can create a process for example, calculating square roots of a number using Pascal. So in this case, the Pascal program becomes the parent process. Why? Because it is the one that is being used by a programmer to create another process that he or she can be using to calculate the square root of a number. And therefore, the Pascal is a child process to the Pascal. You can only be able to run this child process. In other words, you can only be able to execute the process for calculating square roots of numbers after you have loaded the parent process, which in this case is Pascal. And therefore, Pascal is the parent process, or the process that has been created using Pascal, like the one for calculating square roots of numbers, becomes a child process to the parent process, which is Pascal process. After a process is created, both the parent and the child have their own distinct address space. So you can be able, for example, to terminate a child process because it has been assigned its own address space. But if you close or terminate the parent process, you are also bound to terminate the child process. If either process changes a word in its address space, the change is not visible to the other processes. In addition to the processes created at boot time, new processes can be created afterward as well. Remember that most of the processes that are automatically created at boot time are those ones that are meant to play certain roles during a processing period, and mostly they are the system processes, some of which are in charge of controlling the operations of the computer, some of which are the basic utilities processes for ensuring that the user or the system is able to execute routine tasks or housekeeping tasks. Otherwise, the user also creates his or her own processes later, like when he or she runs certain programs or certain applications. Often, a running process will issue system calls to create one or more new processes to help it do its job. Creating new processes is particularly useful when the work to be done can be easily formulated in terms of several related but otherwise independent interacting processes. In interactive systems, users can start a program by typing a command or double-clicking an icon. My dear students and the rest of the learners, note, just as I said in process management part 1, is that if you have a program that has been stored or installed in a secondary storage device, if you want that program to become a process and be useful, you have manager to initialize or start a new process. And one of those ways is by opening it, for example, by double-clicking it or right-clicking on its icon and then clicking on open. When you do that, that is a way of telling the processor or the operating system that you want to change a program to a process so that you can be able to use it to execute or perform the intended task. And therefore, during the operating period, when you're using the computer, you can be able to initialize or run several processes at the same time. And each of these processes has to go through various states. When the operating system decides that it has the resources to run another job, it creates a new process and runs the next job from the input queue in it. Technically, in all these cases, a new process is created by having an existing process execute a process creation system call. And one of the ways of executing a process system or a process creation system call is when you start a program using an icon, for example, from your desktop. That process may be a running user process, a system process invoked from the keyboard or mouse, or a branch manager process. Now, my dear students and the rest of the learners, this simply informs you that we have various ways of initiating a process. One is user-initiated process, and then we have what we call the system-initiated processes. The user-initiated processes are those processes that are invoked by the user, while system processes are those ones that are automatically started by an operating system or the system software for certain purposes during processing period. What that process does, new process. This system call tells the operating system to create a new process and indicates either directly or indirectly which program to run in it. After a process has been created, it starts running and does whatever its job is. So the four principal events that lead to processes creation include: number one, system initialization. Number two, execution of a process creation system calls by a running process. Number three, a user request to create a new process. And number four is initialization of a batch job. In some systems, when a process creates another process, the parent process and child processes continue to be associated in certain ways. The child process can itself create more processes, forming a process hierarchy. A process has only one parent, but 0, 1, 2, or more children. A process and all of its children and further descendants together form a process group. What do I mean? What I mean is, if, for example, you start a parent process like Pascal program, when Pascal is loaded in a system, you move on and you create a child process, which is a program for calculating, for example, square roots of numbers. Then that process for creating square root or calculating square roots of numbers can also be able to create a file that will contain those square roots of the numbers. And therefore, in this case, you will have a parent process, which is Pascal, a child process, which is the process for calculating square roots of numbers, a child's child process, which is a file that contains the square roots of the numbers that has been created by a child process for calculating square roots of numbers. And therefore, that means that you have a parent process with a child who has another child. And then because these three processes are related to each other, they form a process group. And remember, you can have a process also creating several other files, or a child process can create several files, and these files are also processes. When a user sends a signal from the keyboard, the signal currently associated with the keyboard, usually all active processes that were created in the current window. This is signal independent. Individually, each process can catch the signal, ignore the signal, or take the default action which is to be killed by the signal. My dear learners, the most important point for you to note is that when you talk about new state, this is the point at which a process or a program has been prepared to become a process. The user, for example, has issued a system call or a call to run a program, and the program is converted to become a process by being assigned all what it requires, including the creation of the process control block. So the PCB is part and parcel of the new state in as far as processes are concerned. So once a process has been marked as a process, or once a program has been marked to become a process at a certain time, that is the point of that the process is said to have entered its new state. And therefore, either the users or the system itself can invoke a program to become or to be prepared to become a process ready for execution. However, Windows has no concept of a process hierarchy. All processes are equal. The only hint of a process hierarchy is that when a process is created, the parent is given a special token called a handle that it can use to control the child. However, it is free to pass this token to some other process, thus invalidating the hierarchy. When a user requests for a service from the system, the system will first initialize the process, or the system will call it an initial process. So several new operations, or so every new operation which is requested to the system is known as the newborn process. The next state is the ready state. When a process changes its state from one state to another, then it's known as the process state transition. So when a process is created and has met all the requirements to be able to be executed, it transits from the new to the ready state. Therefore, a process is in ready state when it's already in the main memory. It's runnable and it's just waiting to learners. Is that once a process or once a program has been prepared, has been marked to become a process, and the process manager finds out that it has all what it requires to be executed, that the process is now transferred to the main memory, where it joins a queue of other processes. And therefore, the change from the new state to the ready state, a point at which a process is just waiting to be allocated its time of the processor, that is called a process transition. So the process is transiting or changing from the new state to the ready state. And the ready state is found in the main memory. So a process can only join the ready state if it has met all the requirements to be able to be executed. A process is therefore in ready state when it's already in the main memory. It is runnable, but it's just waiting to be assigned the processor by the operating system. Normally, at any one point of the system's execution, there are usually several processes in the main memory waiting for execution. The processes in the ready state are those that have been newly created or have been temporarily stopped from running. That is, they are temporarily removed from the processor in order to let another process run. or those that have been waiting for a certain input or output operation to occur. And that operation has already occurred. And therefore, the processes that are found in ready state are of three types. Number one, those processes that have been newly created, they have transited from the new state to the ready state. The second category of processes that are found in the ready state are those ones that were already running, but they are, for example, due to a higher priority process having arrived in the queue. And therefore, the process with lower priority is removed from the process or from the processor and is taken back to the ready state to wait for the higher priority process to complete its execution or its turn. Number three, it is those processes that had been waiting for an input-output operation, for example, those that had been blocked or suspended temporarily, waiting for an input or output to be made, and that taken place, and therefore they are ready to run. So all the processes that are ready for the CPU are kept in a ready queue. A ready queue is a line of processes that are waiting for their turn, starting from the first one, which is ahead, to the one which is at the back of that queue. The third state is called the running or the executing state. A process which was in a ready state transits to the running state when it gets assigned the processor. And therefore, a process is said to be in running state when it's the one that is being currently executed by the processor. And therefore, it is the process which is in control of the central processing unit at that time. Therefore, once the process has been assigned to a processor by the operating system scheduler, the process state is set to running and the processor executes its instructions. Possession of the processor if the process completes execution or for a given time slice. A running process possesses all the resources needed for its execution, including the processor. A process can run in either of the two modes, which are the kernel mode or the user mode. So what are these modes, or what happens under each of the modes? In kernel mode, the processes can access both the kernel and the user addresses because it allows unrestricted access to hardware, including execution of privileged instructions. In this mode, a system call from a user program links to a switch to kernel mode. In other words, the processes that are running and the kernel mode are those ones that have privileged instructions and they have direct access to hardware. They can access that hardware anytime. In user mode, processes can access but not the kernel instructions and data or those of other processes. The system executes on behalf of a user application and avoids various catastrophic failures. A process that is in running state may be removed from the CPU, that is, may be removed from the running state and be taken back to the ready queue in main memory, that is, be taken back to the ready state if the running process has run long enough, that is, it has occupied or spent its maximum allowable time for an interrupted execution, and it is time to let another process have some CPU time. Or when a higher priority process than the one in running state arrives into the ready state. In other words, we are saying that a process can transit from the running state to the ready state if, for example, it has spent its allocated time slice of the processor and completed it before the process has completed its execution. Secondly, a process that is in running state can be taken back or can transit to the ready state if a higher priority process arrives in the queue and it needs urgent attention. So this kind of transition is called running to ready state transition. The fourth state is called the blocked state. Blocked state is a state whereby a process is unable to run until some external event has happened. So a process is denied possession of the CPU because of not being able to carry on until an external change in state or event has occurred. For example, if a process makes a call to an input or output device that is not currently available, or when a process requires entry or require access to a critical section which must be executed automatically, then such a process will be put in blocked state, waiting for what it has requested for to be provided before it proceeds, so as to give way to those other processes that were in ready state and require to be attended to by the processor. And this helps the processor to avoid being idle. In addition, it is also possible for a process that is conceptually ready and able to run to be stopped because the operating system has decided to allocate the CPU to another process for a while. A process that is in running state is thus transited to the blocked state if the processor discovers that a process cannot continue execution, especially when it initiates an input-output operation before its allocated time expires, thus voluntarily relinquishing the CPU. A process is put into the blocked state if it requests for something which it must wait for. However, a blocked process can transit from the blocked state to the ready state if the external event for which a process was waiting for example, some input happens or arrives. The blocked processes are normally kept in a blocked queue, which we normally call the device queue in main memory. The fifth state is called the suspended versus waiting state. This normally occurs when a process that had been blocked is swapped out or removed from the main memory and taken back to the secondary storage medium like the disk, especially when a process being executed requires more memory. What we are saying is that the difference between the blocked state and the suspended state is that the processes that have been put in blocked state normally queue or do their waiting in the main memory. But if it happens that a process wants to arrive in the ready queue and that the process is lacking capacity and the amount of memory that is available is not adequate to accommodate it, then those processes that had been blocked or put in blocked state and were occupying space in main memory are removed and taken to temporarily to a secondary storage medium from where they can wait from in order to create space for the larger one or for the larger process. And therefore, when a process that had been blocked is removed from the main memory and is put in a waiting state, but in a secondary storage device or on a disk, then that type of state is called the suspended versus waiting state. It can also occur when a process is currently able to run, but for some reason, the operating system has not replaced the process on the ready queue, but has been swapped out from the main memory and placed on external storage medium by the scanner. We are going to look more in depth about swapping when we shall be looking at memory management in memory management topic later on. So from here, the process may be swapped back into the waiting state or the blocked state. Therefore, a process moves into the waiting state if it needs to wait for a resource, just as it is for the blocking state, such as waiting for user input or waiting for a file to become available. Such a process is stored out of memory. And my dear students and the rest of the learners, this is very important for you to remember. That is, that the processes that have been put in the system outside of the main memory, that is in a secondary storage media. But those ones that are put in the blocked state because they are waiting for an event to occur, they are normally kept in the main memory. But if the main memory at any time is not adequate, instead of the processes that have been put in blocked state to continue occupying space in memory, such processes become the candidates for the suspension or suspense state. Therefore, the blocked, if there are ready processes available and the operating system determines that the ready process 8 would like to dispatch, I repeat, therefore, the blocked process transits the suspend/blocked states if there are ready processes available and the operating determines that the ready process it would like to dispatch requires more main memory to maintain adequate performance. A process may also transit from the suspend versus ready state to the ready state when there are no ready processes in main memory that require the operating system to bring in a process in the ready versus suspend state, especially when it has a higher priority than any of the processes in the ready state. In addition, a process can transit from a suspended state to a ready state when a process that had been placed in the ready queue. Normally, the operating system is designed with a preference to suspend a blocked process rather than to suspend a ready process. The following are therefore some main reasons for a process suspension. Number one, swapping. There are times when the process may not have a high enough priority and there is no need for memory. Such processes are swapped out. Process is swapped out of memory and transferred to a hard disk by the memory management system in order to free memory for other processes. Number two is timing. A process may be suspended while waiting for the next time interval. Submit but hold, that is suspend a process until another process has completed. Number three is interactive user request. Processes may be suspended reasons by the user. Number four, parent process request. For example, a parent process may request to modify a child process or to coordinate the activity of various descendants. Number five is processes can be suspended because of other operating system reasons. Like the operating system may suspect that a certain process is causing a problem or may cause or is bound to cause a problem or affect negatively the system performance. And such a process will become a candidate for suspension. The following are some characteristics of a suspended process. Number one, it is not immediately available for execution. Secondly, the process may or may not be waiting on an event. Number three, or thirdly, preventing the execution or to prevent the execution. Process may not be removed from the suspended state until the agent orders the removal. The sixth state is what we call the suspended versus blocked state. In this process, or in this case, a process is both swapped out and blocked, and may be swapped back in again under the same circumstances as swapped out and waiting process, although in this case, the process will move to the blocked state and may still be. A process in the suspend versus blocked state can transit to the suspend versus ready state when the event for which it has been waiting for occurs. This requires the state information concerning suspended processes to be accessible to the operating system. The seventh state is called the terminated or exit state. This is a state whereby a process has been released from the pool of executable processes by the operating system and is waiting to be removed from the main memory. A process may be terminated either from the running state by completing its execution or by explicitly being killed. Killing a process simply refers to that activity or operation whereby a process is suddenly stopped its execution as it is removed from the main memory. That is sudden stoppage of a process before it has completed its operation. Once the process finishes its execution or it is terminated by the operating system, it is moved to the terminated state where it awaits to be removed from main memory. And therefore, this simply means that once a process has completed being processed or it has been halted prematurely before it completes execution, that process is temporarily kept in main memory and then immediately removed from the main memory. A process can transit from a running state to terminate the state when a process has either finished execution or discovers that it cannot continue either automatically or through system call. When a process terminates, its resources are returned to the system. It is punched from the system list of tables or tables, and its process control block is also erased. That is, the process's control block's memory space is returned to a free memory pool. The following are some of the main reasons or conditions that can lead to process termination. Number one is normal exit or voluntary exit. Most processes terminate because they have done their job. Secondly, a process can be terminated as a result of an error. So we call it error exit, and it's also voluntary. For example, a user may try to compile a program that does not exist. Number three, a process can be terminated due to a fatal error, which we call involuntary. An error caused by a process due to a bug in program, for example, executing an illegal instruction referring to non-existing memory or dividing by zero, that can lead to a fatal error, and therefore it can lead to mature or immature or premature termination of a process. Number four, a process can be terminated by being killed by another process. This is also involuntary. So a process executes a system call telling the operating system to terminate some other process. For example, if you are a parent process, which is, for example, a Pascal, and then it happens that you had created a program or a process for calculating square roots of numbers. So using Pascal, which is the parent process, you can easily terminate a process for calculating square roots of numbers even before it has completed its task. So using the parent process Pascal, you can terminate a Pascal program or a Pascal process for calculating square roots of numbers. Let's now move on to process models. A process model is the representation of all the phases through which a process passes from the time of entry into the system until it completes or exits. It is also called a process life cycle. To implement the process model, the operating system maintains a table or an array of structures that we call block with one entry per process. These entries are called process control blocks. These entries contain important information about the process's state, including its program counter, the stack pointer, memory allocation, the status of its open files, its accounting and scaling information, and everything else about the process that must be saved when the process is switched from running to ready or blocked state so that it can be restarted later as if it had never been stopped. The following are therefore some types of process state models or process life cycles. The first one is the two-state process management model. Number two, three states process managed model. Number three, we have 5-state process managed model. We have 6 states. We have the 7-state process managed model. Let's commence by looking at what we call the two-state process management model. In this model, each process moves through 2 phases. The first phase is running, and the second phase is not running. Remember, my dear students and the rest of the learners, that each process moves through a number of phases from its entry into the system until when it completes or exits. But from a process's point of view, a process is either running or it is not running. The reasons for not running have to be maintained by the system for appropriate progress of the process to be gained. Therefore, the two-state process management model explains that a process is either being executed by a processor or it is not. Thus, a process may be considered to be in one of 2 states, either running or not running. When the operating system creates a new process, that process is initially labeled as not running system in the not running state. The process or some portion of it then exists in main memory and waits in the queue for an opportunity to be executed. After some period of time, the currently running process will be interrupted and moved from the running state to the not running state, making the processor available for a different process. The dispatch portion of the operating system will then select from the queue of not running processes one of the waiting processes to transfer to the processor. The chosen process is then relabeled from a not running state to a running state, and its execution is either begun if it is a new process or is resumed if it is a process earlier time. So the following diagram illustrates a two-state process model. And as you can see, my dear students, a process enters, it is lined up in the main memory, waiting for its turn, and then it is assigned the processor. So in this case, a process is viewed to be in 2 states. Anytime when a process is not in charge or it's not holding the CPU, it's tend to be in not running state. But whenever a process has been allocated the processor and it's the one which is being executed, it's viewed as running. And those are what we call the 2 states of a process model. The next process model is the 3 states process managed model. The 3-state process management model introduces a new state that is called the blocked state. This state describes any process which is waiting for an input-output event to take place. In this case, an input-output event can mean the use of some device or signal from another process. The three states in this model are the blocked state. And the following diagram represents this three-state process model. As you can see, my dear students, a process begins by being created. So once the process has been created and it has all what it requires to be ready to run, it's put on the render state, which is in the main memory. So the process joins the other processes that are ready but waiting for their turn to access the processor. Then once their turn arrives, they are dispatched by the dispatcher to the central processing unit where the process gets executed. It continues to be executed, but if its time elapses before it has been processed completely, it is taken back to the ready state where it will then join or wait. And once its time is ripe again, it is dispatched to the running state. But if a process is being executed by the processor, it is in the running state, and then it makes a request for an entry or for some data, for example, that has to be fed by the user, that process will be removed from the running state and placed in the blocked state. Why? Because the processor is not aware of how long it will take before the entry or the input is done. And therefore, that process joins the blocked queue or the blocked state processes. It is put in blocked state, waiting for the input to be made. Once the input or the entry of what the process was waiting for has been done, or once the input has arrived, that process is unblocked, and then it is put now under the render state to join those others that are waiting for their turns. They are ready and they are waiting for their turns. And therefore, that process which was blocked is then executed, or it's taken to the processor to be executed. And once the processing is complete, the process gets terminated from the system. That is what we call the three states process model. That is the ready state, the running state, and the timeout state. The process model is what we call the 5-state managed process model. This process model is almost similar to the 3-state process model, but then in this case, we now introduce or add the new state and the terminated state. So in the new state, the process is created, it is initialized. And once everything that it requires is in place, that the process is admitted into the render queue to join those other processes that are waiting for their turn in main memory. So that the process joins the main memory, it joins the render queue. Once its turn arrives, it is allocated the processor, and therefore, when it is being processed by the processor, it's said to be in running state. However, if the process which was in running state makes a request for an input or output or any other event, it is then put into the waiting or blocked state, where it will wait for the input or output event to occur. Once that entry has been made, the input or output that a process that had been blocked or that had put in waiting state arrives, that process which had been blocked is then taken to the render queue, and it joins those others that are waiting for their turn. And then once their turn arrives, it is taken to the running state. However, remember, if a process has all what it requires and it is in the running state, but then, for example, its time completes before it completes execution, that process will be interrupted and then it will be taken back to the ready queue to wait. And then once its time arrives, it will go back again to the processor. The processor will process it, and once it gets completed, that process will be terminated. It will exit the system. And therefore, this diagram illustrates the 5-state process model. The 5 states are the new state, sometimes called the creation state or initialization state. Then we have the ready state. We have the running state. We have the waiting or unblocked state, and we have the terminated state. The next model is what we call the 6-state process management model. The only addition that has been added into this model is the suspend state. And the same applies. The new state and the new state, a program is converted to become a process. It is marked to become a process. Once it has what it requires to be executed, it joins the ready state. It joins other processes in the main memory that are waiting for their turn to be executed. Once the turn for the process arrives, it is dispatched by the dispatcher to the central processing unit or CPU, where it enters into the running state. So that is, the processor executes the instructions in that process. If the time for that process elapses before the process completes execution, it is interrupted, and then it is taken back again to the ready queue to wait. And once it gets its turn again, it is dispatched to the running state, that is the processor. If it happens that the process makes a request for an entry which is not currently available, like an entry from the user, that process will be put into blocked state. And remember, blocked state is a state where a process has been removed from the process and it is put in the device queue or blocked queue, waiting for an event to occur. If that event occurs, then that process is taken again to the ready state and the process repeats. However, if a higher level process or a process arrives into the main memory and it happens that the main memory is not adequate enough to accommodate that new arrival, what will happen is that the processes that have been blocked and they had occupied the space in the main memory will be removed and they be suspended. And therefore, they'll be swapped out of main memory and they will be stored in a secondary storage medium somewhere temporarily, waiting for the memory to be adequate for them to be activated or being brought in. So once the memory is enough, the process that has been swapped out of memory after it has blocked and it has received what it requires or what it had requested before will then be activated and it will be taken to the ready queue where it will then wait for its turn to go to the running state. Once a process has completed being executed, or for example, an error has occurred or the user has entered an instruction which requires the process to be terminated, then the process will be released from the CPU and it will be released free from all resources and it will be terminated and it will exit the system. And that is what we call the exit state. So the 6 states in 6-state process model are the new state, the ready state, the running state, the blocked state, the suspended state, and finally the exit state. What about the 7-state process model? The 7-state process managed model usually use a portion of the hard disk to emulate main memory. And this, therefore, requires additional states to describe the state of processes which are suspended from main memory and placed in virtual memory on disk. Such processes can, at a future time, be resumed by being transferred back into the main memory. So, when we talk about the 7-state process managed model, it's important, my dear learners, to remember or to note that usually the use of a portion of the hard disk to emulate the main memory requires additional states to describe the state of processes which are suspended from main memory and placed in virtual memory on disk. Such processes can, at a future time, be resumed by being transferred back into main memory. A process can thus be suspended from the running, ready, or unblocked state, giving rise to two other states, namely the ready or versus suspend state and the blocked suspend state. A running process that is suspended becomes ready, suspend, and a blocked process that is suspended becomes blocked, illustrates a 7-state managed process model. This is the model. As you can see, my dear students, just like it was for the other models, a process begins with a new state. It is prepared and joins the ready state. Then it is dispatched to the running state. If it makes use or it makes a request for an event or an entry that requires to be made, that process will be blocked. And if it happens that the main memory is not adequate to accommodate more blocked processes, those blocked processes will be suspended, and then they'll be put in what we call the blocked suspend state, which normally takes place outside the main memory in a storage medium. If a blocked suspended process receives an entry that it was waiting for, but still the main memory is not enough to accommodate that new process, inasmuch as that process will have received the input or the entry it required, that the process that was in block suspended state will now be placed under the ready suspended state, meaning that the process, yes, is ready to be executed. It has all what it wants, but it cannot be able to join or to enter or to be swapped in into the main memory because the space in the main memory is not adequate. But once the space in memory is adequate, in main memory is adequate, the process which was now in the ready but suspended state, that means it was ready, but it was outside the main memory, it will be brought in, that is, it will be activated, and then it will join the ready state, and the process will continue that way. And therefore, my dear students and learners, it's good to note that the blocked suspended state and the ready suspended state, both of these states or these processes takes place outside the main memory. These are found, these two states are found in a secondary storage medium, but a space which has been set aside for temporary use for processes that have been blocked or suspended. They have been blocked, but they're suspended. That means they're outside the main memory. And once the process that was blocked, waiting for an input, is done, but it was suspended, it then joins or put in another state that we call the ready but suspended state. And once the main memory is now adequate, the process which was in ready but suspended state will be activated and it will join the ready state. It's also important to note that a process might have been in the ready state in the main memory, but because another process has arrived which or is arriving which has a higher priority than those ones which are in the queue, and the main memory is not adequate to accommodate all of them, a process which was in ready state will be taken out of main memory and be put under the ready suspended state to create room for the new arrival. So the reason of this process being removed from the ready state and being suspended to the ready suspended state, that means it has been removed from the main memory and transferred temporarily into a secondary storage medium, temporarily waiting to be brought back. It's not because that process had any issues. It's not because it had made any request, but it has just been taken out in the same ready state, but in a suspended state. That means outside the main memory for the purposes of creating space for the new arrival if the memory is not adequate. So this section in the secondary storage medium that is used for processes that are in ready suspended state and blocked suspended state are treated. These memories or these spaces in secondary storage media are treated as if they are extension of the main memory. So sometimes you call them the virtual memory, which you're going to learn more in our third topic on memory management. So once a process has completed its execution or it has been halted prematurely, that process will be removed from the running state and it will be released. And therefore, it will be exited from the system through the exit state. So the 7 states are the new state. A process can proceed from the new state to the end state, to the running state, to the exit state, or it can move from the end state. These are transitions. It can transit from the end state, new state, to the end state, to suspended state. A process can also move from the new state, then it is directly suspended, and then it is taken to the ready state. From the ready state, it's taken to the running state, and finally to exit state. A process can also be created and is new. It joins the ready queue. When it is there, it goes to the processor. And then if its time elapses before it completes being processed, it is taken back to the ready state. A process that is also running can be put in the blocked state, then go to the ready state. It can be removed from the blocked state and put in blocked suspended state. Then it can move to the ready suspended state. And then from there, it can be taken to the ready state. So my dear students and learners, it is good to understand these transitions. So like the 7-state process model, it has several transitions like new to ready to running to exit, new to ready to running to ready to running to exit, new to ready to running to blocked to ready to running to exit, new to ready to running to blocked suspend to ready suspend to ready to running to exit. The most important point for you to remember, my dear students, is that every process will begin with the new state and it will end with the exit state. So whichever transition you're going to have in this kind of a model, it must begin with, every transition must begin with the new state and it will have to terminate with termination stage or the exit state. Good. Let's now look at the process, the scheduling. When a computer is multi-programmed, it frequently has multiple processes or threads competing for the CPU at the same time. This situation occurs whenever two or more of them are simultaneously in the ready state. If only one CPU is available, a choice has to be made as to which process to run next. The part of the operating system that makes the choice or that makes the choice is called the scheduler. And the algorithm it uses is called the scheduling algorithm. It's called the scheduling algorithm. The process scheduling is the activity of the process manager that handles the removal of the running process from the CPU and the selection of another process on the basis of a particular strategy. Process scheduling is an essential part of a multi-programming operating systems. Such operating systems allow more than one process to be loaded into the executable memory at a time, and the loaded process shares the CPU using time multiplexing. The two types of processes, according to length, classified according to the length of the CPU burst, and when I talk about the burst, is the time it takes for the CPU to attend to a certain process under the running state. So the two types of processes classified according to length of the CPU burst are: one, compute-bound processes, and number two is input-output bound processes. So what are compute-bound processes? These are the processes that spend most of their time computing and have long CPU bursts and infrequent input-output waits. Number two is input-output bound processes. These are processes that spend most of their time waiting for input or output, and thus they have short CPU bursts and frequent input-output waits. They are input-output bound because they do not compute much between input-output requests, not because they have especially long input-output requests. A key issue related to scheduling is when to make scheduling decisions. The following are the main situations in which scheduling is needed. Number one, when a new process is created, a decision needs to be made whether to run the parent process or the child process. Since both processes are in ready state, it is a normal scheduling decision and can go either way. That is, the scheduler can legitimately choose to run either the parent or the child next. Number two is when a process exits. If a process can no longer run, since it no longer exists, some other processes must be chosen from the set of ready processes, and therefore this process that is no longer running has to leave the system. And if no process is ready, a system supplied idle process is normally run. Number three, scaling is important when a process blocks on an input-output for any reason. Number four, scaling is important when an input-output interrupt occurs. If the interrupt came from an input-output device that has now completed its work, some process that was blocked waiting for the I/O may now be run or be made ready to run. It is up to the scheduler to decide whether to run the newly ready process, the process that was running at the time of the interrupt, or some burnt process. The operating system maintains all process control blocks in a process scheduling queue. The operating system maintains a separate queue for each of the process states And the PCBs of all processes in the same execution state are placed in the same queue. When the state of a process is changed, its process control block is unlinked from its current queue and moved to its new state queue. This means that there are usually several queues. There are queues for processes in the ready state, queues for processes in running state, queues for processes in blocked state, etc. The operating system maintains the following important process scheduling queues. The first queue is called the job queue. The second is the ready queue. The third one is the device queues. So what is a job queue? This queue keeps all the processes in the system. The ready queue keeps a set of all processes that are residing in main memory. They are ready and they are waiting to execute. So every new process is always put in this queue. The third queue are the device queues. The processes which are blocked due to unavailability of an input-output device constitute this queue. So this queue is not normally called the blocked queue. All the processes that have been blocked, instead of being sent to have been placed in a blocked queue, they are sent to be placed under the device queues because they are occupying memory and they are waiting for an input or an output event to occur. And that concerns making use of certain devices. My dear students and learners, this is an illustration of these queues that I have already mentioned. So we have the job queue, and job is placed in a ready queue. From the ready queue, it is taken to the central processing unit to be attended to. In case its time elapses, it's taken back to the ready queue. In case a process is in the running state or a job is in the running state holding CPU, and it makes a request for an entry that needs to be made, for example, by the user, it is blocked and therefore it is placed in the IO waiting queue, or what we are calling the device queue. And then from there, it is assigned what it had requested for. So those which have been assigned what they have requested for are placed under the IO queue. Then from there, once they are ready and there is adequate space in main memory, they are taken to the ready queue. And that continues until when a process exits. The operating system can use different policies to manage each queue, and some of them include the first in, first out, round robin, priority, amongst others that we are going to learn in this subtopic. The operating system scheduler determines how to move processes between the ready and run queues or running states, which can only have one entry per processor call on the system. In the above diagram that we have looked at, it has been merged with the CPU. A good process scheduling algorithm should possess the following features or characteristics. Number one is fairness. This is giving each process a fair share of the CPU. Comparable processes should get comparable service. A scheduler makes sure that each process gets its fair share of the CPU and no process can suffer indefinite postponement. Number two is policy enforcement. If the local policy is that safety control processes get to run whenever they want it to, even if it means delaying others, the scheduler has to make sure that this policy is enforced. And this can mostly apply to the antivirus or security processes. Number 3 is balance. This is keeping all parts of the system busy when possible. If the central processing unit and all the other input-output devices can be kept running all the time, more work gets done per second than if some of the components are idle. So it's better to keep the whole system running at once by a careful mix of processes. Number 4 is throughput. This is maximizing jobs per hour. So a system's throughput is the number of jobs done per unit time that the system completes. Number 5 is turnaround time. It's always important to minimize the time between the submission of a process and its termination. It measures how long the average user has to wait for the output. It is the length of time between when the job arrives in the system and when it finally finishes. It includes actual execution time plus time spent waiting for the resources, including the processor. Number 6 is efficiency, what we call CPU utilization. It's always important that the process manager keep the CPU busy all the time. And therefore, the algorithm that is going to be applied, the scaling algorithm that will be applied should ensure that the CPU is busy all the time. The scaler should keep the system or the CPU 100% busy all the time when possible. If the CPU and all the input-output devices can be kept running all the time, more work gets done per second than if some components are idle. Number 7 is waiting time. This is the sum of periods or total time that is spent by processes while in the ready queue. It's equal to service time minus arrival time. The response time is number 8. It's always important for a scaling algorithm to minimize the response time by responding to requests quickly. It is the time from the submission of the request until the response or output begins to be received. Often, the process can begin producing some output to the user while continuing to process the request. It's the length of time between when the process arrives in the system and when it starts to produce output. Then we look at penalty ratio. The scaling algorithm applied should ensure that the penalty ratio for a system is not very high. Penalty ratio is the elapsed time divided by the sum of the CPU and input-output demands of the job. If the job never had to wait for another job, could allocate each input-output device as soon as it wants, and experience no overhead for other operating system functions, it would have a penalty ratio of 1.0. However, if it takes twice as long to complete as it would do in a perfect system, it has a penalty ratio of 2.0. Then we have proportionality. It is always important for the scaler or the scaling algorithm applied to ensure that the system meets the user's expectations. Then the next one is deadlines, that is, meeting deadlines. It's always important to ensure that no data is lost. Therefore, when a process completion deadline is specific, the scaling discipline should subordinate other goals to that of maximizing the percentage of deadline. So processes should be able to meet the deadlines. Then we have predictability. Always avoid quality degradation in multimedia systems. So what is embossed? Embossed is the computation done by a process between the time it becomes ready and the next time it blocks. So which are the main types of schedulers that undertake the work of scheduling? Schedulers are a specified system software which handle processes scheduling in various ways. Their main task is to select the jobs to be submitted into the system and to decide which process to run. The three types of schedulers are therefore the long-term scheduler, the short-term scheduler, and the medium-term scheduler. The long-term scheduler is also called a job scheduler. It determines which programs are admitted to the system for processing. It selects processes from the queue and loads them into memory for execution. Process loads into the memory for CPU scheduling. So the primary objective of the job scheduler is to provide a balanced mix of jobs, such as input-output bound and the processor bound. It also controls the degree of multiprogramming. If the degree of multiprogramming is stable, then the average rate of process creation must be equal to the average departure rate of processes leaving the system. When a process changes the state from new to ready, then there is use of long-term scheduler. So in other words, the long-term scheduler is in charge of process creation and ensuring that the process becomes ready and joins the ready queue. So the transition of a process from the new state to the ready state is the work of the long-term scheduler. The short-term scheduler is also called a CPU scheduler or a dispatcher. Its main objective is to increase system performance in accordance with a chosen set of criteria. It is the change of ready state to running state of the process. The CPU scheduler selects a process among the processes that are ready to execute and allocates CPU to one of them. The short-term schedulers, therefore, make the decision of which process to execute next. The short-term schedulers are faster than long-term schedulers. So in other words, it is the short-term scheduler that is in charge of process transition from the ready to the running state. The medium-term scheduler is the scheduler that removes processes from memory and swaps them. It is thus a part of swapping. It reduces the degree of multiprogramming. It's in charge of handling the swapped out processes. A running process may become suspended if it makes an input-output request. A suspended process cannot make any progress towards completion. So in other words, it is the work of medium-term scheduler to translate the processes from the running to the blocked state, or from the blocked to suspended state, or suspended to ready state. In this condition, to remove the process from memory and make space for other processes, the suspended process is moved to the secondary storage. This process is called swapping, and the process is saved. Swapping may be necessary to improve the process mix. The following diagram illustrates how a medium-term scheduler functions. As you can see, my dear students and the rest of the learners, a process, first of all, joins the ready queue. Then it is dispatched by the short-term scheduler to the CPU. A process that is currently being executed can be swapped out, partially executed, or swapped out processes. In other words, the processes that have been assigned to the running state, if, for example, their time elapses before they get completed, they are swapped out. So those that are partially executed after they have been attendant to can be swapped out. That means they can be taken out of main memory and be stored temporarily in a secondary storage medium. Afterwards, they are brought in from the secondary storage medium to the render state or the render queue. In addition, a process which is currently being executed can be put under the input output waiting queues. That is, it can be blocked. And then it joins the IO waiting queue. And once it is provided with what it requires, it joins the input output queue for the render processes. Processes that have been blocked, but they have gotten the data that they were waiting for, and therefore they are transferred to the render queue. That's how the scalar, the medium-term scalar, will work. The following are the main functional components or parts of the scalar. Number one, a queuer. It adds a pointer or reference to the process's process control block as per the desired data structure of the render queue, which is usually a collection of linked lists. Number two, dispatcher. It is the part that implements the scaling algorithm to pick the next process to run. Number three is the context switcher. It loads the selected process onto the CPU as the running process. The following diagram, therefore, illustrates the parts of a scalar, and we have already discussed this in depth. As you can see, my dear students, a process can move from any other state, and then it becomes ready. So it joins the render queue. This process is then enqueued. It joins the render list. From there, it is dispatched. It is allocated some time to join the CPU, and therefore it is dispatched to the CPU. So it is converted, or its state is changed from the render state to the running state, and therefore it makes use of, it gets hold of the CPU. Such a process, or after the process is through, after the CPU is through, it can go back, or an instruction can be sent by a dispatcher to pick another process from the render queue. And once it is picked, the process continues, but then it is also assigned various information, various details concerning the context switching, then dispatching, and the rest. The following is the comparison of the three scalars: the long-term scalar, the short-term scalar, and the medium-term scalar. Number one, it is the job scalar, that is the long-term scalar is the job scalar, or the short-term scalar is a CPU scalar, and the medium-term scalar is a process swapping scalar. Secondly, the long-term scalar has a less speed than the short-term scalar, when the short-term scalar is faster than the long-term scalar and the medium-term scalar. However, the medium-term scalar speed is in between the long-term scalar and the short-term scalar. Number three, the long-term scalar controls the degree of multiprogramming in the system, while the short-term scalar provides lesser control over degree of multiprogramming, while the medium-term scalar reduces the degree of multiprogramming. Number four, the long-term scalar is almost absent or has minimal time sharing, or in other words, it is almost absent or minimal in time sharing system. The short-term scalar, on the other hand, is also minimal in time sharing system, while the medium-term scalar is part of time sharing systems. Number 5, the long-term scalar selects processes from a pool and loads them into memory for execution. The short-term scalar selects those processes which are ready to execute, or the medium-term scalar can reintroduce the process into memory and execution can be continued. So which are the main scaling algorithms or decision modes? These can be divided into 2 categories with respect to how they deal with the clock interrupts. These are the non-preemptive scaling algorithms and the preemptive scaling algorithms. So let's begin with the non-preemptive scaling algorithms. These are scaling disciplines in which once a process has been given the CPU cannot be taken away from them until they run to completion. The algorithm picks a process to run and then just lets it run until it blocks, either on an I/O or waiting for another process, or until it voluntarily releases the CPU. In effect, no scaling algorithm are made during, or no scaling decisions are made during clock interrupts. After clock interrupt processing has been completed, the process that was running before the interrupt is resumed, unless a higher priority process was waiting for a now satisfied timeout. Examples of these scaling algorithms are shortest job first, that is SJF, or shortest job next, that is SJN. Fast come, fast served, that is FCFS. Multi-level queue scheduling, multi-level feedback queue scheduling, and priority scheduling. The following are therefore some characteristics of non-preemptive scheduling algorithms. Number 1, the short jobs are made to wait by longer jobs, but the overall treatment of all the processes is fair. Number 2, the response types are more predictable because incoming high priority jobs cannot displace waiting jobs. Number 3, a scheduler executes jobs when a process switches from the running state to the waiting state, or when a process terminates. What about preemptive scaling algorithms? This is a scaling discipline or strategy of allowing processes that are logically runnable to be temporarily suspended by taking away the CPU without having run to completion. It picks a process and lets it run for a maximum of some fixed time. If it is still running at the end of the next time interval, it is suspended and the scheduler picks another process to run if one is available. Doing preemptive scaling requires having a clock interrupts occur at the end of the time interval to give control of the CPU back to the scheduler. Preemption is essential to keep one process from hogging the CPU and denying service to the others. Examples of these scheduling algorithms are round robin, shortest remaining time, that is SRT, multi-level queue scheduling, multi-level feedback queue scheduling, and priority scheduling. So let's look at each of these algorithms at a time. We begin with the fast come, fast served algorithm. It is also called fast in, fast out, or FIFO, run to completion, or run until done. processes are assigned the CPU in the order they request for it. Basically, there is a single queue of ready processes. When the first job enters the system from the outside, it is started immediately and allowed to run as long as it wants to. It is not interrupted because it has run too long. As other jobs come in, they are put into the end of the queue. When the running process blocks the first process on the queue that has been in the queue the longest time is run next. When unblocked process becomes ready, like a newly arrived job, it is put on the end of the queue. With this algorithm, a single linked list keeps track of all ready processes. Picking a process to run just requires removing one from the front of the queue. Adding a new job or unblocked process just requires attaching it to the end of the queue. Although the first come, first served is simple, it performs poorly in terms of global performance measures, such as CPU utilization and throughput. It also gives lousy response to interactive jobs, which tend to be input-output bound. In addition, if one process gets into an infinite loop, it will run forever and shut out all the others. It is poor in performance as average wait time is high. The good thing about fast come, fast served is that there is no starvation. Every burst does get served if it waits long enough. It's therefore fair, easy to understand, and equally easy to program. The following are examples for fast come, fast served. So in this table, we have several processes. One, we have process A that has arrived at time 0 and it requires to be processed for 3 or a burst of 3. Process B arrives at time 1 and it has a burst of 5. Process C arrives at time 3, it has a burst of 2. Process D arrives at time 9 and it has a burst, or it has to take 5 being in the processor. Processor E arrives at the time 12 and it has a burst of 5. The following Gantt chart shows the schedule that results from fast come, fast served scheduling. Remember, my dear students and the rest of the learners, we have said that in fast come, fast served, processes are assigned the processor based on their arrival. So each process has to wait for the previous one to be executed. And therefore, process A will take a total time of 3 to complete execution. Process B will be executed and complete at time 8. C at time 10, D at time 15, and E at time 20. So the following is the computation for the waiting time and the penalty ratios for these jobs. So process A arrives at time 0. It requires to take or to be processed for a burst of 3. And therefore, because these processes are being attended to based on fast come, fast served, because it has arrived at time 0, it will straight away start being processed at time 0. So it will not wait for so long on the queue. In fact, it will not wait. It will arrive at time 0 and it will start being processed at time 0. And because it has a burst of 3, it will finish being executed at time 3. And therefore, the penalty ratio for this process will be 1.0. It will be 1.0. Then process B arrives at time 1. It has a burst of 5. So process B will start being executed at the time when the first process completes execution. That is time 3. Therefore, it will start being processed at time 3. So it arrived at time 1, but then it will start being attended to at time 3. So the waiting time for that process will be the starting time minus the arrival time. The starting time minus the arrival time, which gives 2. So the penalty ratio for this system will be 1.4. Therefore, the finishing time will be 8, while it has started being executed at time 3. It will take a period of time of 5. Therefore, it will be 3 plus 5 to give 8. Then process C will arrive at time 3. It will require a time of 2 to be processed. So it will start after the first process is complete. So its starting time will be 8. Then it will finish being executed at time 10 because it is the finishing time is equals to the starting time plus the burst time. The starting time plus the burst time. So the finishing time will be time 10. The waiting time will be 5. That is the starting time minus the arrival time. So the penalty ratio will be 3.5. 3.5. Then process D arrives at time 9. It has a burst of 5. The starting time, it will start being processed once process C is completed. Therefore, the finishing time will be 15 because it is the finishing time is equals to the starting time plus the burst time. It will have a waiting time of 1 because it will arrive in the system and wait for just 1 minute. Remember, you get 1 by subtracting the starting time minus the arrival time. So the penalty ratio for D will be 1.2. Then we have process E. Arrival time is 12. It has a burst of 5. So it will start at time 15, which is the time when process D will finish. And then it will finish being executed at time 20 because it will require a burst of 5. The waiting time will be 3 because it is the starting time, which is 15, minus 12, which is the arrival time. And therefore, this process will have a penalty ratio of 1.6. The average, therefore, waiting time for this system will be 2.2. How do you get the average waiting time? It is the total waiting time for all the processes divided by the number of processes, which is 0 plus 2 plus 5 plus 1 plus 3 divided by 5. That is 0, 2, 7, 8, 11. So 11 divided by 5. 11 divided by 5. That will give 2.2. And the penalty ratio is just the same. You add the penalty ratio for each of the processes, you divide by the number of processes. Therefore, you will get the penalty ratio, the average penalty ratio for the system, which is 1.74. So the shorter the burst, the worse is the penalty ratio. A burst that doesn't wait before being processed usually has a penalty ratio of 1.0. Good. So let's move on and look at example 2. This example, we have 4 processes: process 0, process 1, process 2, and process 3. Those are 4 processes. Process 0 arrives at time 0. It requires execution time of 5. And in this case, therefore, it requires a service time of 0. Process 1, arrival time is 1. Execution time is 3. And service time is 5. Process 2 arrives at time 2. Execution time is 8. Service time is 8. Process 3, arrival time is 3. Execution time is 6. And service time is 16. So this simply means that if a process arrives at time 0 and its execution time is 5, then simply put, it will start being serviced immediately. The process 1, which has execution time of 3, will have to start its execution time at time 5, which is the time for the previous process to execute. Process 2 will have a service time of 8. Will have a service time of 8, which means it will have to wait for the previous process to be serviced. And that means the service time will be 8. And then, of course, which is the execution time. And then process 3, arrival time is 3, execution time is 6, service time is 16. So how will these processes be attended to? So for the first process arrives at time 0. It requires execution time of 5. So it will complete being executed at time 5. Then process 1 will kick in. Process 1 has arrived at time 1. And the burst time for process 1 is 3. And therefore, process 1 will complete at time 8. Then process 2 arrives at time 2. And this processing time is 8. And therefore, it will be completed at time 16, which is 8 plus 8. And then process 3, which arrived at time 3, has a burst of 6. And therefore, it will complete being processed at time 22 because it is 16 plus 6. What will be the waiting time for each of the processes? What will be the waiting time for each of the processes? So waiting time is equals to service time minus arrival time. So process 0 arrives at time 0 and its service time is 0. Therefore, the waiting time will be 0. Process 1 arrives at time 1. Its service time is 5. So its waiting time is 4. Process 2 arrives at time 2. Its service time will be at 8. And therefore waiting time will be 8 minus 2, which is 6. Process 3 arrives at time 3. It starts to be serviced at time 16, meaning it will have waited for 16 minus 3, which is 13. And the average waiting time for this system will be 0. Waiting time for process 0, waiting time for process 1, waiting time for process 2, waiting time for process 3, and then waiting time for process 4. Remember, this is waiting time for the first process, process 0, waiting time for second process, that is process 1, waiting time for the third process, which is process 2, waiting time for the fourth process, which is process 3. Then all of them divided, the total waiting time divided by the number of processes, giving the average waiting time as 5.75. Then let's look at the second algorithm, which is shortest job first. It is also called shortest process next, or SPN. Shortest job next, SGN, or shortest burst time first, SBF. It is an algorithm in which waiting job or process with the smallest estimated runtime to completion is ran next. In other words, when CPU is available, it is assigned to the process that has the smallest next CPU burst. The SJF scaling is especially appropriate for bunch jobs for which the runtimes are unknown in advance. Since the SJF scaling algorithm gives the minimum average time for a given set of processes, it is probably optimal. It is worth pointing out that shortest job first is only optimal when all the jobs are available simultaneously. When several equally important jobs are sitting in the input queue waiting to be started, the scheduler picks the shortest job first. By decreasing average waiting time, we also improve processor utilization and throughput. The shortest job first algorithm favors short jobs or processors at the expense of longer ones. It is the best approach to minimize waiting time. The obvious problem with SJF scheme is that it requires precise knowledge of how long a job or a process will run, and this information is not usually available. It's easy to implement in bunch systems where required CPU time is known in advance, but it's impossible to implement in interactive systems where required CPU time is not known. Example of how this algorithm is used is, if you have 4 jobs, A, B, C, and D, with run times of 8, 4, 4, and 4 minutes, respectively, by running them in the order as the order in figure A below. The turnaround time for A will be 8. The turnaround for A will be 8 minutes. The turnaround for B will be 12 minutes. For C will be 16 minutes. And for D will be 20 minutes. And the average of this system will be 14 minutes. In other words, we are saying if process A, B, C, and D were to be processed according to their order of arrival, that is first come, first served, then process A will take a duration of 8 minutes. Then process B, which takes 4 minutes, will complete being executed at time 8 plus 4, which is 12. Then process C will complete being processed once A and B is over. So it will start being processed once A and B are through, and therefore it will take 4. And that means it will complete at time 8 plus 4 plus 4, that is 16. And process D, which will require 4 minutes to be processed, will be completed execution at time 20, which is 8 plus 4 plus 4 plus 4. So that will give an average system time of 14 minutes. So that means 8 plus 12 plus 16 plus 20 divided by 4. That will give us an average of 14 minutes. However, if we run those jobs using the shortest job first, as shown in this table, then the turnaround time will now be 4 for process B, 8 for process C, 12 for process D, and 20 for process A. And the total average time for this system will be 11, because it is 4 plus 8 plus 12 plus 20 divided by 4, giving an average of 11 minutes. In this case, what has been done is that the processes that are shorter have been attended to first, and the processes that are longer have been attended to later. So because we had process B, process C, and process D, all of them having a time of 4, then each of them will be attended as if they are first come, first served. So in this case, B will be attended to first, followed by C, followed by D, in as much as all of them have the same amount of time or amount of processing time. And therefore, process A, because it's the largest, or it is the one which will take more time to be processed, is attended to after B, C, and D is over. Another example for our processes, we had our process 0, whose arrival time was 0, execution time was 5, and the service time was 3. Process 1, arrival time was 1, execution time was 3, service time 0. Process 2, arrival time is 2, execution time is 8, service time is 16. Process 3, arrival time is 3, execution time is 6, service time is 8. So based on the amount of time each of them will get being executed, According to the algorithm of shortest jobs first, the first one to be attended to will be P1, which has execution time of 3, followed by P0, which has execution time of 5. Then it will be followed by P3, which has execution time of 6. And lastly, the one which will be processed being the last is P2, because it has a longer execution time of 8. And therefore, in this case, the order of execution will be P1, P0, P3, P2. Therefore, that means process P1, whose arrival time was 1, will be attended to immediately. It arrives, and it will take, it will complete being execution at time 3. It will complete being executed at time 3. Then process 0 will complete being attended to at time 8. That is 3 plus 5. Then process P3 will complete being executed at time 16, which is time 3 plus 5 plus 8. And then the last process, process P2, will complete being executed at time 22, which will be execution time of P1 plus execution time of P0 plus execution time of P2, and then plus its own execution time of 8. That will be 3 plus 5 plus 8 plus 6, giving 22. What about the waiting times for each of these processes? Remember, we have said waiting time is equal to service time minus arrival time. So process P0, remember, we have said the first process to be attended to will be process 1. And therefore, its service time will be 0 minus arrival time, which is 0. And that will give 0. Process P0 will start being serviced at time 3 once process 1 is through. And therefore, its arrival time is 0. So the waiting time will be 3 minus 0. Process P2, let me go to process P3. Process P3 will be serviced or start being serviced as time 8. It will have waited for time 3, that is for P0 to complete. And therefore, the waiting time will be 5. Then lastly, we have process P2, whose servicing time will start at 14 after the other processes have completed being serviced. Then its arrival time was 2, so its processing, its waiting time will be 12. And therefore, the average waiting time for this system will be 3 plus 0 plus 14 plus 5, giving you 22 divided by 4, which is the number of processes, and therefore that will give us a waiting time of 5.50. The third algorithm is called the shortest remaining time next, or SRTN. It is also called the shortest remaining time first, SRTF. This is a preemptive version of the SJF, in which whenever a new job enters the ready queue, the algorithm reconsiders which job to run. If the new arrival has a burst shorter than the remaining portion of the current burst, the scheduler moves the current job back to the ready queue to the appropriate position, considering the remaining time in its bursts, and runs the new arrival instead. With SRTF, starvation is possible. A very long burst may never get run because shorter bursts keep arriving in the ready queue and run almost immediately. In SRT scheduling, the process with the smallest estimated runtime to completion is run next, including new arrivals. The SRT must keep track of the elapsed time of the running process and must handle occasional preemptions. The turnaround time, waiting time, and others of processes can be easily calculated using a graph as follows. So in this graph, we draw the arrival time or we indicate the arrival time for each process and its burst time. So we have process 1, like in this case, we have process 1, whose arrival time is 0 and the processing time is 1. So because it's the first one to arrive, it will start at time 0 being executed, and it will take a burst of 1. And therefore, it will exit from the system. Now, how do we draw this scale? So for us to be able to arrive at this scale, we add all the times for each burst. That is the burst for each process. In this case, we have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3. That is 1, 3, 6, 10, 15, 21, 22, 24, 27, 31, 32, 34, 37. And therefore, on the uppermost side of our scale, we shall have that 7. So this is the cumulated total bursts for all the processes in our system. That is that 7. And we begin at 0. So we list the times on this side of our axis. And then on this other one, we list the processes together with the arrival time and the burst times. So in this system, we have P0, arrival time is 0, burst time is 1. Process 2, arrival time is 0, processing time is 2 or burst time is 2. Process 3, arrival is time 0, processing time or burst time is 3. Process 4, arrival time is 0, burst time is 4. Burst time is the time which it takes for a processor to complete the execution of a process. Then process 4 arrival time is 0, processing time is 5, and that continues. So from process P1 to P5, all of them arrives at time 0. So in our map, we indicate the arrival time for each of them when they have arrived. So this line here, this is the time for arrival time. But now the question is, at what point will the process begin being executed? At what time? Will it start being processed? And how long does it take in the CPU? Remember, each CPU or each process requires certain time in the processor to be executed. So the first process arrives at time 0, it will be the first one to be processed, and therefore it will complete being executed at time 1. After which, process P2 will commence, and it will be processed for a burst of 2. So it will complete being processed at time 3. After which, the process will start being executed, and it will take a burst of 3. That is up to time 6. Then, all this time, process P4 is waiting. So it will start being executed, and it will be processed for a total time of 4. And then process 5 or process P4 will start being executed, and it will take a burst of 6. And then at that time, another process which has been waiting all through P5, which requires a burst of 6, will then require to be processed. Note that process P5 starts being processed at time 15. And therefore, after just 1 minute, of being processed, another process arrives in the system, which is process P6, which has a burst of just 1. So at this time, at time 16 here, process P5 will be having a burst of 5, while process P6 has a burst of 1. And therefore, once process P6 arrives and the process P5 has been processed for just 1 minute, it will have to be removed from the running state so as to accommodate, because it has a burst of 5. It has a burst of 5, so that it can create a space for the process which has a burst time of 1. And therefore, process P5 will be altered with a balance of 5. And therefore, process P6, which has arrived at time 16, will be processed for just 1 minute. So it will not even wait. And then it will be exited from the system, after which process P7 also arrived at time 16, so it will just wait for 1 minute. And then, because in comparison to process P5, it has a burst of 2, while P5 has a burst of 5. So process P16 will be processed for the 2 minutes. It will be processed for the 2 minutes up to time 19. Now, at this time still, we have process P5 with a burst of 4 or 5. But process P16, process 8, arrives at time 16 and it has a burst of 3. And therefore, because it is shorter than process P5, it will be processed. It will be allocated the processor. And then process P8, which also arrived at time 16, as a burst of 4. So process P5 is still having a burst of 5, while process P8 has now a burst of 4. So what will happen? Process P8 will be allocated the processor and it will run for 4 minutes. And then it will exit the system. So at this point, there is no any other process in the system up to time 26. Up to time 26. And therefore, at this point, our process P5, will be processed for 1 minute. So it will be remaining with a burst of 4. At that same time, when our process P5 has just been processed for 1 minute, there is a new arrival. So process P9 arrives at time 27 with a burst of 1. So our process P5 will be removed again from the process with a burst of 4. And therefore, it will give room for process P9 to be processed for 1 minute. And then because the other process P10 also arrived at time 27, and it had a burst of 2, it is the one which will be processed because process 5 is remaining with a burst of 4. So 4 and 2 So it means that process 10 will have a higher priority. So it will be processed for a time 2. And then a new process has arrived at time 27 also. And it has a mass of 3. So it is one which will be processed before process P5. And therefore, it will be processed for 3 minutes. At that point now, because there's no any other process in the system, our process P5 with a balance of 4 will be processed now from time 3 to time 7. And at this time, all our process will have been processed. In this diagram, note that we always indicate the time of arrival of each process. The time of arrival of each process. So these are the times of arrival. And then we indicate, we change the burst time, or the time when the CPU is processing or attending to a process, with a different change, different from the time for waiting. Like these are times for waiting, times for waiting, times for waiting. However, there are processes without waiting, like process P1. There is no waiting time here. There is no waiting time. Even this process has no waiting time. This process here has no waiting time. So that's how we use the Gantt chart to represent and to calculate the various times for processes. The fourth algorithm is called the round-robin scaling algorithm. It is the oldest, simplest, fairest, and most widely used algorithm. In this algorithm, processes are dispatched in a FIFO manner, but are given a limited amount of CPU time that is called a time slice or a quantum, which it's allowed to run. If the process is still running at the expiry of its quantum, the CPU is preempted and given to another process. If the process is blocked or finished before the expiry of its quantum, the CPU is given to another process. Therefore, round-robin keeps all the bursts in a queue and runs the first one like first come, first served. But after a length of time, Q, called a quantum, if the current burst hasn't completed, it is moved to the tail of the queue and the next burst is started. So to implement this algorithm, the scaler maintains a list of runnable processes. When a process uses up its quantum, it is put on the end of the list. The major consideration in this algorithm is the length of the quantum. Since context switching also takes time, if the length of the quantum is short, the CPU will spend more time doing context switching rather than doing actual processing work. To improve the CPU efficiency, we should set a longer quantum time, but not too long, since it will cause poor response time. Switching from one process to another requires a certain amount of time for doing the administration, saving, and loading registers and memory maps, updating various tables and lists, flashing and reloading the memory cache, and so on. Setting the quantum too short causes too many process switches and lowers the CPU efficiency, but setting it too long may also cause poor response to short interactive requests. A quantum around 20 to 50 milliseconds or microseconds is often a reasonable compromise. It is very effective. It is a very effective algorithm in time-sharing environments in which the system needs to guarantee reasonable response times for interactive users. The success or failure of round-robin scheduling depends on the length of the time slice or time quantum. If the slices are too short, the cost of context switching becomes high in comparison to to the time spent doing useful work. If they become too long, processes which are awaiting spend too much time doing nothing. And in the worst case, everything reverts back to first come, first served. A rule of thumb is to make the time slices large enough so that only, say, 20% of all context switches are due to timeouts. The remainder occur freely because of waiting for requested output. The following graph illustrates how processes are scheduled using round-robin scaling algorithm. So in this case, we still have our processes. So as usual, on this side of the scale, for you to come up with this scale, you add the burst times for each process. You add the burst times for each process so that you can be able to come up with this maximum value here. So in this case, you can see our total burst time for this system will be 1 plus 2, that is 3, 7, 13, 21, 29, 35, 39, 41, 42. And that's is 42 on this side. Because that is the time when the last system will exit from the system. And then we have the arrival times. So we indicate here the process and its arrival time plus burst time. So in this case, we have process 0, P1 to P10, and each has its arrival time and its processing time. But what I want you to note, my dear students and the rest of the learners, is that each of the process will be allocated a maximum of 3 burst size, or a maximum burst of 3 to be attended by the processor at any given time. So the same thing we have done for the other algorithm. Using the chart, you indicate the arrival times. So the arrival times for process P1 to P5 is time 0. So process 1 will be processed for 1. So it will be processed for 1. All that time, process P0 or P2 will be waiting. As you can see here, it is waiting. Process P0 is waiting. So it will have waited for 1 minute, and then it will be processed for 2, a burst of 2, or for time 2. Then process 3 has been waiting, so it will wait until process P1 and P2 are through. And then it will be allocated the processor, and it has a burst of 4. But note that each process is only allocated a burst of time 3. So it will be processed for 3 minutes, for example, and the remainder of 1 will be pendent. So it will be taken back the queue to wait. But as it has been taken back the queue, it will find out that process P4 also arrived at time 0. So once process P3 has completed its burst of 3, remainder 1, then process P4 will be attended to. P4 has a burst of 6, so it will be allocated its 6, it's 3 first, then it will be left with the remainder of 3. Then process P8, which has been waiting, once process P4 is through, process P5, which has a burst of 8, will be attended for 3, a burst of 3. Then it will remain with a burst of 5. So at this point, before this process gets completed, there's a new arrival, or we have another set of arrivals. So at time 11, process P6, P7, P8, P9, and P10 arrived. So what will happen is once process P5 has been processed for 3 and it is remaining with 5, then process P6, which has a burst of 8, will be given its 3. Then process P7, and therefore it will remain with what? With a balance of 5. Then process P7, which arrived at time 11, will also be allocated its slice of 3. Then the balance of 3 will wait. Then next, process P8 will be allocated its slice of 3, and it will remain with 1. Then process P9, which also arrived at time 11, will be given a slice, and the P9 has time slice of 2, so it will be processed to completion. And then at that time, process P11, which has a burst of 1, it will be processed for 1. At this time, so at time 24, a number of processes exited. So the process that unbalanced is starting with P3, which had a balance of 1. Then process P4, which had a balance of 6. Process P5 had a balance of 5. Process P6 had a balance of 5. Process P7 had a balance of 3. P11 had a balance of 1. They will now be attended to again based on their arrival in the queue. So the first process to be attended to, which has of course been waiting for quite some time, will be process 3. Process 3 had a balance of 1, so it will be allocated the processor, and therefore it will complete being attended to at time 25. At that point, the next process to arrive, which was P4, which had a balance of 3, will be executed for 3 minutes. Then it will leave the system. And then the next process, P5, which had a balance of 5, will be given its 3, and then it will remain with a balance of 2. Then the next process to be attended to will be P6, which had a balance of 5. So it will be allocated the first its 3, and then it will be left with a balance of 2. Then the next process, which is of course in the queue, is P7, which had a balance of 3. It will be allocated, it will be processed, it will be allocated its slice of 3, and it will complete being executed. Then the next process, which had a balance of 1, was P8. It will be attended to for a time slice of 1, and it will exit in the system. So at time 38, there are 2 processes that have not yet completed being executed. That is process P5 with now a balance of 2, and the process the P6, which has a balance also of 2. So they will again be attended based on their order in the queue. So P5, which has waited for a little bit longer, and it is the first one now in the queue, it will be allocated as 2, time slice of 2, and it will leave, then it will complete being executed. And then lastly, we are going to have process 6, which has a burst time balance of 2. It will be attended to, and therefore at time 42, all the processes will have been completed. Therefore, my dear students and the rest of the learners, you do the same. So if you want to know the amount of waiting time for each process, for example, waiting time for process P3, it will be this waiting time here from time 0 to 3 plus time 6 to 24. That is now 24 minus 6 plus 3 minus 0. So you'll get waiting time. This is waiting time for this process, and then waiting time up to here. So the accumulated waiting times for a process like process P3 will be the first waiting time. This will be the first waiting time, and the second waiting time. There are processes which will have waited for more. Like, for example, process P5 has waited from time 0 to time 9, then from time 12 to time 28, and then from time 31 to time 38. So you add these waiting times here for this process. You add these waiting times. Sorry, you add these waiting times here and here. Then you get the total. Then to calculate the total burst, of course, which is well indicated like 8, is you add this burst plus this burst plus this burst or time slice. Good. That's how easy it is for you to use a chart. And if you wanted to calculate the total waiting time for the entire system, just add all these balances, and these times, and these times, and all of them for each process. These ones that have a certain color for waiting time, and all of them, all the way. So you add this, and you'll be able to get it right. Total burst, you add the dark ones. The other. Therefore, if you were asked, for example, a question like how many times has the process, for example, P7 been allocated the processor, how many burst times? Like P7 has 2 burst times, this burst time plus this burst time. So those are 2 burst times. But specifically, how long? What is the total size of the burst? You just add this one plus this one. And therefore, using a chart, you can easily tabulate various types of times. The next algorithm is called priority scheduling. In this algorithm, each process is assigned a priority or order of importance, and the runnable process with the highest priority is allowed to run first. This priority can be defined either internally or externally. Internally defined priorities use some measurable quantities or qualities to compute priority of a process. The following are examples of internal priorities. 1 is time limits. 2, the memory requirements. Number 3, the file requirements, for example, the number of open files. Number 4, the CPU versus I/O requirements. The following are also examples of externally defined priorities that are set by criteria that are external to operating system. Number 1, the importance of a process. Number 2, the type or amount of funds being paid for computer use. Number 3, the department sponsoring the work. Number 4, politics. Priorities are assigned dynamically by the system to achieve certain system goals. For example, some processes are highly I/O bound and spend most of their time waiting for I/O to complete. Whenever such a process wants the CPU, it should be given the CPU immediately to let it start its next I/O request, which can then proceed in parallel with another process actually computing. Making the I/O bound process wait a long time for the CPU will just mean having it around occupying memory for an unnecessary long time. Priority scheduling can be either preemptive or non-preemptive. A preemptive priority algorithm will release the CPU if the priority of the newly arrival process is higher than the priority of the currently running process, while a non-preemptive priority algorithm will simply put the new process at the head of the ready queue. To prevent high priority processes from running indefinitely, the scheduler may decrease the priority of the currently running process at each block or each clock tick, at each clock interrupt. If this action causes its priority to drop below that of the next highest process, a process switch occurs. Alternatively, each process may be assigned a maximum time quantum that it is allowed to run. When this quantum is used up, the next highest priority process is given a chance to run. Priorities can also be assigned to process statically or dynamically by the system to achieve certain goals. It is often convenient to group processes into priority classes and use priority scheduling among the classes, but round-robin scheduling within each class. For example, in this diagram, you can see that we have several processes. So the processes with a similar priority are placed together in one queue. So we have processes that have priority 1, second priority, then the priority, fourth priority. So processes are organized in various queues based on their order of priority. So that those ones with the highest priority, those who have the highest priority, are attended to first, and those with the lowest priority are meant to run. If you have, for example, 3 processes in the highest priority, because they have equal priority, they will be attended to in their order. For example, of arrival, first come, first served, because they have equal priority. So when all the processes arrive in the system, they are first of all categorized in various queues based on their priorities. Those with a similar priority are put in one queue. Those with the next priority are put in the next queue in that order. And then each of those queues or processes in each queue will be attended to based on either the order of arrival. And if each process is being allocated a certain burst, then each process based on their order of arrival will be given a portion or a time slice. And once that time slice is over, that process will be taken back to that same queue and then wait for the next one to be completed, and they will continue in round-robin manner. And therefore, that's why we are saying that priority algorithm is both preemptive and non-preemptive. If processes are in the same queue and they have the same priority, they will be attended to either in the first come, first served basis, where a process is being attended to up to completion. But if each process is supposed to use the CPU for just a specific amount of time or a quantum, then the processes will continue rotating in round robin until each queue is completed, and then the processes in the next higher priority will be attended to. That's very important to note. Like in this case now, we have several processes. We have process P0, P1, P2, and P3. Each of them has arrival time, execution time, the priority, and the service time. So in this case, those processes with priority of 1, those priorities with a priority of 1, 2, and 3 will be attended to based on the priority. So the one which has the highest priority will be attended to first. For example, in this case, our process P3 has the highest priority, followed by P1. And then P0 and P2 have similar priority. So process P3 will be attended to first, and it will be processed for a time of 6. That is, it will execute for time 6, which is this one. And therefore, it will get completed. Once it gets completed, the next process, the second level priority, will be process P1, which is supposed to be executed for time 3. So it will stay, and it will get completed at time 9. At this time now, we have P0 and P2, which have equal priority. And therefore, P0 has execution time of 5, while P2 has execution time of 8. So P0 will be attended to first. So it will run from time 9 all the way time 14. That is execution time of 5. Once that is done, then process P2 will be allocated its time, and it will run for 6 time slice of 6, or it will run for a time of 6 up to time 22. In this case, my dear students, you can see that this is priority algorithm, but the processes are each being attended to up to completion. So in this example, this is a priority algorithm which is non-preemptive because each process is being attended to up to completion. So how do we calculate the waiting time for each of the processes? We do it in the same way that we did for the others. Process P3, because it has the highest priority, it will start being serviced at time 0. Its arrive time is 0. So the waiting time is 0 minus 0. Then we have the next process, which is the next process in the queue is process P1. It has arrived at time 6. Service time is 6. Arrival time is 1. So waiting time will be 5. So simply, process P0, it will start being serviced at time 9. Arrival time was 0. So the total waiting time will be 9. Process P1, service time is 6. That's when it will start being serviced. It arrived at time 1, so it will have waited for 5 time 5. Process P2 will start being serviced at time 14. So it arrived at time 2, so it has been waiting for 12. P0 will start being serviced at time 0. It arrived at time 0, therefore waiting time is 0. So simply put, in this case, process P3 will have the shortest waiting time, followed by the second one, which was according to the order of priority, that is P1, then P0, and the last process will be P2. The average waiting time for this system is 9 plus 5 plus 12 plus 0. Then the figure that you get, that is 9, 14, 26, 26 divided by the number of processes in the system, that will give 6.5. A major problem with priority scaling is indefinite blocking or starvation. A solution to the problem of indefinite blockage of the low priority process is aging. Aging is a technique of gradually increasing the priority of processes that wait in the system for a long period of time. The second scaling algorithm is what we call multiple level or multi-level queues scaling. Multi-level queues are not an independent scaling algorithm. They make use of other existing algorithms to group and schedule jobs with the common characteristics. Multiple queues are maintained for processes with common characteristics. Each queue can have its own scaling algorithm, and the priorities are assigned to each queue. The following is an illustration of how these queues can be ordered. So in this case, from this diagram, the priorities are the same as the priority algorithm that we have looked at, but the system processes have the highest priority. Then they are followed by interactive processes, then interactive entity processes, bunch processes, and the processes with the lowest priority are the user processes. So when the priority processes arrive, they are categorized based on their types. Those user processes have the lowest priority, but the system processes have the highest priority. So the process scaler then alternatively selects jobs from each queue and assigns them to the CPU based on the algorithm assigned to the queue. Simply, what this means is that once all the processes have arrived, they'll be categorized based on their types. And then the scheduler will start attending to each process based on the queue that it is in. Those in the highest priority queues will be attended to first, and those in the lowest priority queues will be attended to towards the end. Since processes do not move between the queues, so this policy has the advantage of low scheduling overhead, but it is inflexible. Number 7, we have multi-level feedback queues, also called MLFQ. It allows a process to move between the queues, and it uses many random queues and associate a different priority with each queue. The algorithm chooses to process the queue with the highest priority from the occupied queue and run that process either preemptively or non-preemptively. If the process uses too much CPU time, it will be moved to a lower priority queue. Similarly, a process that waits too long in the lower priority queue may be moved to a higher priority queue. Multi-level feedback queue scheduler is defined by the following parameters. Number 1, the number of queues. Number 2, the scheduling algorithm for each queue, which can be different from FIFO. Number 3, the method used to determine when to promote a process to a higher priority queue. Number 4, the method used to determine when to demote a process to a lower priority queue. And number 5, the method used to determine which queue a process will enter when that process needs service. This scheduling algorithm is intended to meet the following design requirements for multi-mode systems. Number 1, give preference to short jobs. Number 2, give preference to input-output multi-processes. Number 3, separate the processes into categories based on their need for the processor. In this algorithm, we maintain a sequence of FIFO queues, numbered starting at 0. New bursts are added to the tail of the queue 0. We always run the burst at the edge of the lowest numbered non-empty queue. If it doesn't complete within a specified time limit, it is moved to the tail of the next higher queue. Each queue has its own time limit. 1 unit in Q0, 2 units in Q1, 4 units in Q2, 8 units in Q3, etc. This scheme combines many of the best features of the other algorithms. It favors short jobs since they will be completed while they are still in low-numbered, high-priority queues. Long bursts, on the other hand, will be run with comparatively few expensive process switches. The idea can be generalized. Each queue can have its own scheduling discipline, and you can use any criterion you like to move bursts from queue to queue. There is no need to the number of algorithms, or there is no end to the number of algorithms you can dream up. The following diagram illustrates this type of algorithm. So from this diagram, my dear students and the rest of the learners, you can see that you can have processes that have a quantum of 8. They will be attended to, and then below it, you have those ones with a quantum of 16. And then finally, you have the processes being served according to their order of arrival, where you have the first come, first served, a process or algorithm being applied to attend to the processes. Unlike multi-level queue scaling algorithm, where processes are permanently assigned to a queue, multi-level feedback queue scaling allows a process to move between queues. This movement is facilitated by the characteristic of the CPU burst of the process. If a process uses too much CPU time, it will be moved to a lower priority queue. This scheme leaves IO-bound and interactive processes in the higher priority queues. In addition, a process that waits too long in a lower priority queue may be moved to a higher priority queue. This form of engine also helps to prevent starvation of certain lower priority processes. The last one is multiple queues. Processes are set up in priority classes. Processes in the highest class are ran for 1 quantum. Processes in the next highest class are ran for 2 quanta. Processes in the next class are ran for 4 quanta, and so on. Whenever a process used up all the quanta allocated to it, it's moved down 1 class. And with that, my dear students, we have come to the end of this presentation. You can now proceed to video part 3, which covers interprocess communication, deadlocks, resource allocation graphs, and error diagnosis. This video is part 2 of the 4 videos on operating systems process management. Therefore, once you are through with this video, advance your knowledge in process management by listening to part 3 and part 4 in the series from Emily Swap ICT YouTube channel. You can also access more videos on various ICT/computer topics by visiting and subscribing to Emily Swap ICT YouTube channel. In addition, for you to be able to access free life skills, motivational, and inspirational resources, kindly visit Emily Swap Motivation YouTube channel. For any further correspondence, kindly write to us through the email emilyswap@gmail.com. Thank you very much and be blessed. Let's meet in part 3 of this series on operating systems process management. Thank you.